Okay, today we're going to talk about the state pattern. And we're going to talk about the state pattern because they are particularly useful for these things called event-driven systems. And an event-driven system is one that must react to incoming events in a timely fashion. So events can occur at any time and in any order. Another name for these types of systems is reactive systems. So a GUI is reactive. The GUI must be able to handle any user interaction and has really no idea what's going to come next. Many military jets have a fly-by-wire system that's not mechanical in nature. So there's the software running in the jet that monitors the state of the yoke and the other controls used by the pilot and sends messages to the engines, the wing, the tail. This is also a reactive system because it's monitoring the pilot and reacting to their actions. Now, we're going to talk about these things called state machines. State machines are an excellent way of specifying and implementing event-driven systems. So a system exhibits stateful behavior when it operates differently during different periods of time, and when that behavior can be partitioned into finite, non-overlapping chunks called states. So being in a state means that the system responds to only a subset of allowed inputs, produces only a subset of outputs, and changes state to only a subset of other possible states. Okay, so this will start to make sense shortly when I draw a state machine diagram. In other words, a state is a period of time during which the system will wait for certain events to happen and then will respond with certain behavior. An event is an occurrence in time that has significance to the system, and when one of these events occur, there may be a transition to a new state. And when a transition occurs, one can add an action to be executed upon the transition. State machines are an effective tool because the behavior is dependent on a certain type of event that occurs and the history of the system. So state machines record the history, what has happened in the past in your system. Okay, so we're gonna look at a few state machines. Let me start by kind of showing you what goes in a state machine diagram. First, we have these things called states, and in a state machine diagram, we usually have a rounded rectangle, and then inside the rounded rectangle, we put the name of a state. So here we have two states, state 1 and state 2. Transitions are drawn between states. So a transition is marked with an arrow from the starting state to the ending state. And this just means we're going to move from this state to this state. Each transition has an event that caused it, an optional predicate guard, and one or more actions that should happen when the transition is made. Okay, so here's one transition from state 1 to state 2. There might be another transition from state 2 back to state 1. And what we would do is we would mark what is the event that causes this transition. So if you're in state 2 and this event occurs, you will move from this state to this state. Now, remember I said there's an optional guard. Basically what that means is there's some condition that can be checked that says if we're in state 2 and this event happens, we'll only make the transition if this optional guard evaluates to true. So we put some kind of Boolean condition in here. And also I said when this transition happens, we can have one or more actions that occur when that transition is made. Okay, so let's look at a state machine. I'm going to draw a state machine for my microwave oven. Okay, so my microwave probably works similar to some of yours, where it's basically, most of the time it's in this idle state, where the microwave is not doing much. Okay. There's another state called entering time. So in my microwave, you have to click this button to say that you want to set the time, and then you type in a number of seconds, and then you can hit the start button, and that'll start the microwave will start cooking. Okay, so if you're in the idle state and you hit this button called set time, okay, that's the event that if that happens while in the idle state, we will make a transition into this state called entering time. Okay, if we're in the entering time state and somebody hits the cancel button, okay, that's going to cause a transition back to the idle state. Okay. If you're in the idle state and somebody hits set time, we'll cause the transition here. And then when you're in the entering time state, you can enter in some numbers. Okay, so there's a numeric keypad with 10 digits. And notice here we have a self transition. We start in the entering time state, and when somebody hits the number, we're going to transition out and then right back into the entering time state. Now, why would we ever want to do this? Well, again, you could put some action here. If you want to react to the clicking of the buttons, you can do that on this transition. Okay, we also have a state called cooking, and this is when the microwave is doing its thing. So only after you have entered the entering time state and you hit the start button will we make this transition. And here the action might be to start the oven. Okay. So usually these actions end up being methods or little bits of code that get called. Okay, when we're in the cooking state, the way we end the cooking state, well, somebody can hit the cancel button. And once they do that, not only do we want to make the transition, but we want to stop the oven. Okay. Now, obviously, there's the other way we'd exit the cooking state is if some timer expired. Right? So if I'm cooking something for 60 seconds, after 60 seconds, we should also make the transition back to idle. Okay, so time is an interesting thing in a state machine. So I'm just going to ignore that for now. But you could simulate it with some kind of timer that injects the event after a certain period of time. Okay, so let's look at this. I really like this type of diagram, right? Because it kind of describes everything that has to happen in this state-based system. So, for example, in the cooking state, you only really need to worry about or respond to one event, the cancel event. You can ignore the set time and the start button and all the numbers. If you're in the cooking state and you hit any one of those buttons, we basically just can ignore it. Okay? And this is a strength of state machines. It allows you to ignore things that are not important to a particular state. And this makes these diagrams very simple to create and understand. Now, there is a way to specify an initial state with an initial transition. So initial transitions, you draw a big black dot, and then that always leads into your starting state. And there's no real event that causes that to happen. This just says when the system starts, we're going to go to idle, and then we're going to start responding to certain events in the system. Okay. The state machine really does record the history of the system. I mentioned that before. You can only get to the cooking state, for example, by first going through the entering time state. So if the state of the system is ever here, we know something about the history of the interaction, the user interaction with the system. So we must have started an idle and somehow got to entering time and then pressed the start button. We know a little bit about the history of this system. Okay, we're going to come back to this state machine shortly, and I'll show you some code. But I want you to kind of design a state machine or practice designing a state machine. So imagine an automatic garage door opener. Okay, I'm sure almost all of us have some kind of garage door opener in our houses. Okay, the garage door opener is typical. So obviously there's a garage door. Okay. And then we have cars, right? Maybe we have a car in our driveway here. And every car has a little sensor, right? A little sensor with a button. And there's only one button, right? There's not an open and close, it's just one button. And similarly, there's this track, right, that the garage door slides on this track. Okay. And then, of course, there's some way to control the garage door opener from inside the garage. So we have these little, again, just a single button usually attached to the wall where your garage is, where you walk in the house from the garage. Okay, so basically, this is a super simple system. You just click the button that'll either open or close the door. Another thing modern garage door openers they have these little sensors, okay, that send like some kind of infrared light, and when somebody crosses that barrier, that sends a special signal that can be used. Okay, and this is really for safety, so that if the door is closing and a small child is underneath the door, the door won't crush the child. Okay, so that's kind of the system I want us to model with a state machine. I want you to now pause the video and take a moment to think about the states and the events, and then try and build a state machine that would describe exactly how your typical garage door opener works. Okay, so hopefully you've paused and made an attempt at drawing the state machine. Let me show you kind of what I came up with. Okay, so when I design a state machine, I start by thinking of, well, what are the events that are most important? And the events that I've thought about are a button press. Okay, this can either be on one of the remote controls or on the garage wall. Again, it's basically just one button. You can press this one button. Another event that's interesting is crossing the sensor. Okay, then I think about states or periods of time when the system must react to these events. And here are some of the initial states I thought about. Well, obviously the door can be open, so that's a period of time. The period of time when the garage door is fully open, we call that the open state. And similarly, there's another period of time when the door is shut. We call that the closed state. Okay, but then there's these intermediate periods, right? So when the door was closed and then somebody hits the button. Well, for a short period of time, the door is neither open nor closed, but it's opening. Okay. Again, these are all periods of time. And similarly, when the door is open and somebody hits the button, well, for a short amount of time, we're in a closing state. Okay, so let me start to draw some of these states. So we'll have open, we'll have closed. Our intermediate states we'll put over here. So we'll call this one opening. And over here we'll have closing. Okay, so now I go through each state and I think about, well, what should the system do, if anything, with each of the events in each one of these states? Okay, so let's think about this. These are my states, and these are the events that I'm interested in. Okay, so when the door is closed, so when I'm in this closed state, and a button press occurs, the state machine should move to the opening state, and the motor should start pulling the door up. Okay, so we're in closed, somebody hits a button. So the event is going to be called button, and the action that we want to happen is we want the motor that controls the door to basically pull it up. Okay. When the door is totally open and a button press occurs, the state machine should move to the closing state, and the motor should start to pull the door down. Okay, so we're in open. If somebody hits the button, the action that we want to do is have the motor pull the door down. Okay, but now I'm looking at these states, closing and opening, and I know that when I go from open to closing, at some point I need to go to closed, fully closed. But right now I don't have an event for that, so I think I'm going to add that event. Maybe door fully closed. Okay, so that definitely is an event. That's something of interest that happens in this system. And we really need it here because that's going to control the transition from closing to fully closed. And of course there's going to be an action associated with this. We're going to turn the motor off. Okay, the motor that's pulling the door. Okay, so we're in the open state, somebody hits a button. Okay, that makes us enter the closing state where the motor is pulling the door down, and then once the door is fully closed, we're going to transition to the closed state and the motor is going to turn off. Okay, similarly, on this transition from opening to fully open, we need another event when the door is fully open. And again, the action that we'll take is we'll turn the motor off, once we get to the fully open state. Okay, so it's not likely that you imagine all the events correctly the first time. Sometimes you discover them as you kind of draw the picture. That's totally okay. Okay, let's think about some other things that might happen here. When the door is opening and a button press occurs, okay, what usually happens in that case is instead of opening, the door starts closing, or at least that's how it works in my garage door opener. So if we're in opening and we get this button press, okay, well, we're going to transition from opening directly to closing, because we're not fully open or closed at that point, and we have to start pulling the door down, so we're going to motor down. Okay. When the door is closing and a button press occurs, well, the state machine should move to the opening state, and the motor should pull the door up. Okay, so we're in closing, somebody clicks the button, then it's going to move to opening and start pulling the door up. Okay, we have one more kind of really important event. That's the safety, the sensor. So when the door is closing and somebody crosses the sensor, okay, that's an indication that somebody might get hurt if we continue to close the door. We might crush someone. So when the door is closing and a crossing the sensor event occurs, the state machine should move from closing to opening, and the motor should start to pull the door up. Okay. Okay, so if we're in the closing state only, right? If the door is opening and we cross the sensor, it doesn't matter. If the door is fully open or fully closed and we cross the sensor, again, that doesn't matter. It's only when the door is closing and we cross the sensor do we have to do something. And we're going to transition to opening and then motor up. Okay. So if you have a fancy garage door opener, then when you cross the sensor while the door is open, for example, it might turn a light on. Sadly, I don't have such a fancy garage door opener, so we'll ignore that case. Now this picture is really a great tool. It really describes the entire behavior of the system. Okay. Now, I actually prefer these pictures to a very long textual description of what a garage door opener should do. I could certainly write all the things that my garage door opener does, and it might take a couple paragraphs of text, but that's nowhere near as clear, at least in my opinion, to looking at this one state machine. With this state machine, I really can get a sense of what is supposed to happen at every single chunk of time, period of time. Okay, so I'm a big fan of state machines. I love state machines. The state pattern provides a way to take a state machine, take a drawing like this, and turn it into code. And this is actually a fairly mechanical process. Once you have the picture, once you have the state machine, you can apply this pattern and you actually get a functional system. Okay, so let's look at the state pattern. The intent is to allow an object to alter its behavior when its internal state changes. Okay, so state machines are all about behavior and having different periods of time when the behavior is different. Now the motivation here, the key to this pattern is to introduce a state class to represent the different states an object can be in. And each event that can be handled in the state machine should be a method in the state class. And then subclasses of the state class are going to implement specific behavior. And then lastly, we're going to have this context object that maintains a reference to the current state and is going to delegate all requests to the current state. Okay, so let's look at the structure here. Again, we start with the state class, and this is going to be a generic class that we're going to have a method for every single event that can occur. There'll be a method in the state class. And then the concrete states are going to extend that class and then provide specific behavior for each one of the events. There's going to be a context class that maintains a reference to one of the states. So it's going to be a generic state reference, but it could point to a concrete state A or concrete state B. And then when something interesting happens, when somebody makes a request of the context, okay, all we're going to do is we're going to take the current state reference and ask it to do something. Okay, we're going to introduce an event and let the current state, whatever it's pointing to, handle that event. Okay, so let me draw the class diagram for our microwave system. Okay, so we're going to start out with this class called microwave state. Okay, and the idea is we're supposed to create a method for each one of the events that could happen in the state machine. So let me go back to the state machine for a second. Okay. We had just a couple different types of events. We had set time, cancel, number, and start. Okay. These are all the events that are handled in the state machine. So in our generic state class, we're going to put a method for each one of those events. So we'll have cancel, start. There's an entering time button or event. And then lastly, entering in some number on the numeric keypad. Okay, now what we're going to do with this generic state is we're going to extend it with our actual concrete states. So remember, we had 3 states: idle, entering time, and cooking. So those are going to be our 3 subclasses. So I have an idle class. Entering time. And cooking. Okay, and then we're going to have this this class called the context class. So in my particular case, I'm going to call this context class basically the microwave. Okay, and the microwave class will have a reference to a generic microwave state called current state. Okay, and then what I'm going to do, you'll notice in the picture here, the generic pattern says the context state is going to have a collection of states. You could do that. I'm going to choose instead to use the singleton, and I'm going to make each concrete state a singleton, and that's going to make it so that I won't need this collection of states. That should make a little more sense in a second here. Okay, now to the outside world doesn't know about the state machine. Okay, the outside world is going to interact with the microwave by just calling methods. So maybe there's a press start, press cancel, press entering time, and press number. Okay, so what's going to happen is I'm going to have some kind of GUI class is going to know about the microwave, but it only knows about this interface: press start, press cancel. Okay, and the microwave knows about the state machine. This is kind of hidden. Right? The GUI just knows that there are these methods that it can call in the microwave, and the microwave kind of hides the fact that there's a state machine underneath. Okay, so let me first start by running the program just to show you what it does. Okay, so here's my little GUI. I have a numeric pad. I have a start, cancel, and set time. And I also, in my console window here, you can see that the starting state is idle. Okay, so maybe I could go back to the state machine. Okay, so you'll see the starting state is idle. Now if I were to hit a number, right? In the idle state we don't handle number. That's similar to cancel, right? We don't do anything with cancel, we don't do anything with start. The only thing that will cause a transition out of idle is if we hit the set time button. Okay, and this says we're in idle, we're handling the enter time event, and we're transitioning to entering time. Okay, so now, if, for example, I hit set time, that's ignored because there is no transition out of entering time with the set time event. Okay, if I hit cancel, that'll take me back to idle, and again, it'll ignore number presses until I hit set time. That will take me from idle to entering time again. Now I can start to hit some numbers. Right, so I'm in entering time, and if I hit a number, that's causing this transition right back into entering time. And you'll see my action, I'm kind of building up this string of digits to represent the time. Okay, so I'm in entering time. If I hit the start button, you'll see I'll go from entering time to the cooking state. Right? And you can imagine turning the microwave oven on, and maybe turning the light on, and starting a timer. Okay. Again, it will, in this cooking state, it ignores everything, okay, but the cancel button. So when I hit the cancel button, that's going to generate a cancel event, and that's going to take us back to idle. Okay, and now we've made the full group of transitions through the state machine. Okay, let's look at some code. Okay, let's start with the microwave state. Okay, this is that generic. When I say generic, what I mean is the cancel, start, entering time, and number methods, they're not going to do anything. Okay, only in the subclasses, only in the derived classes will we override these methods to provide some behavior. So microwave state provides these methods that basically just print out the error message. So we have microwave state. There's a method for each event in the state machine. And we start out by just putting an error message in each one of the methods. Okay, next, let's look at a concrete state. Maybe we'll start with idle. Okay, so the idle state extends microwave state. That means it absorbs those 4 default methods, and we have the option of overriding those methods. Also, you'll notice I made this class a singleton. I'll explain that in a second. But if we look at the state machine, when you're in the idle state, really the only method that you respond to, or the only event that you respond to, is entering time or set time. So when you're in the idle state and somebody hits the set time, that should cause a transition to the entering time state. And we'll see that's exactly what happens here. So I'm only overriding enter time. I'm going to absorb the other methods for free, the ones that have that error message. And here I'm just simulating doing some stuff here. So I say I'm in idle right now. I'm handling the enter time event, and then I need to change state. So that's one of the purposes of the context class. Remember, the context class has a reference to the current state, and we need the context class so that we can change state, because we want to go from idle, which is what we're in now, into the entering time state. So this is why we made all these state singletons. We can just pass in the state that we want to move to in the change state method. And then I do another print here that says we're transitioning. And of course I could do real things here. This is where those other actions might go. Okay, next we have entering time. Okay, again, entering time extends the generic microwave state. It also is a singleton. Okay. And in entering time we respond to a number being pressed. So we have to tell the context, the microwave object, to basically append this new, the value of this new number, which we get from the keyboard, and that gets passed into this function. We're going to append that to the current time string. Okay, so every time a number is pressed, we're building up this series of digits. Okay, and notice we don't have to change state. This was that self transition. Now, if somebody hits the start button when we're entering time, okay, well, what we're going to do is we're going to check to see is the time string empty. So this is like a condition. I think I forgot to draw that in the state machine. Right. So what this says is, if you're in entering time and somebody hits the start button, only if the time is set will we make this transition to the cooking state. Okay, so conditions basically end up being ifs inside your methods here. So if the time string is not empty, we will clear it out and change state to the cooking state. If the time string was empty because we haven't clicked any buttons, well, then we would just ignore the start until somebody hits a button. And then lastly, we have this cancel. If we're in entering time and somebody hits the cancel button, we're going to transition back to idle. And lastly, the last concrete state is the cooking state. That again extends microwave state. It is a singleton. Okay. And the only event that we respond to in cooking is the cancel event. And what we're going to do here is change state back to idle. And of course, if this were a real microwave, we'd turn off the oven and maybe turn off the light. So the context class holds a reference to the current state, and then when somebody interacts with the context class, it basically just sends a message to whatever the current state is. Okay, so that context class was called microwave, and we have a private microwave state reference called current state. So this might point to idle, it might point to cooking, it might point to entering time. We have that time string. Again, any data that you want to store about the state machine has to go in the context class. And we always pass the context class into the methods that represent events. Okay, so when I create a microwave, the first thing I do is I change state, and I get the one and only reference to the idle state. So the change state, all it does is it takes a state and it will set the current state equal to the state that gets passed in. So the way you set an initial state is in the constructor, you just call change state and you pass in the state you want to start in. Okay. Then we have these four methods: press start, press cancel, press enter time, press number. And all we do is we say current state, start, because this represents somebody pressing the start button. So if we're in the idle state, that will be handled one way. If we're in the entering time state, that will be handled a different way. If we're in the cooking state, that will be handled yet another way. Okay, this is true for all these different types of events. We just take the current state and tell it what has happened, and we let the state handle that particular event. Okay. And then lastly, we have just some getters and setters for the time string. And again, because I made each one of the states a singleton, I didn't need to have references to each of the states. If I didn't do the singleton, I would have 3 different references to idle, cooking, and entering time. And when I change state, I'd have to kind of check to see if that's a valid state and set the current state equal to it. Okay, lastly, the last class is the driver. This is just a GUI that has all those buttons. Okay, so the driver has a reference to the microwave object, the context object. And all this is kind of uninteresting GUI stuff. The action performed handles the button presses. So when somebody presses the start button, we just tell the microwave to respond to press start, press cancel, press entering time, and pressing a number. Okay, so that's the code for the state pattern. Let's talk about the consequences here. Using the state pattern, it localizes state-specific behavior into these classes, these concrete state classes, and partitions it into different states. The good thing about this is it makes transitions very explicit. There are no messy ifs and Boolean variables to control the state. And this is typically how a naive programmer would deal with excessive state. So if you ever find yourself introducing many Booleans to control what happens in a program, and you have all these ifs that say, well, if this is true and this other Boolean is true, then we want to do this. Chances are you're probably better off creating a state machine and using the state pattern. Some other consequences: the state objects can be shared between different programs. It's somewhat difficult to add and remove states and transitions once you have the state pattern implemented. And of course you can use the singleton for the state objects. That saves you from having to maintain a series of references to concrete states. Okay, I really like the state pattern. I think it's a great way to implement state-based systems, event-based systems, reactive systems, of which there are quite a few. Maybe not running on our laptops, but embedded devices tend to be kind of simple and state-based. And for that, the state pattern is just an excellent way to implement that behavior.